We're diving into something truly mind-bending today, an absolutely fascinating intersection of quantum physics, biology, and medical innovation. We're talking about measuring the temperature of something so impossibly small, it pretty much defies traditional science. We're going to explore a brand new, highly precise quantum thermometer designed to operate entirely inside a living cell.
So think about this for a second. How do you take the temperature of a single microscopic cancer cell? It sounds like a riddle, right? But this is a monumental challenge that biophysicists have literally been trying to solve for years. You can't exactly stick a tiny mercury thermometer under a cell's tongue. We need something infinitely smaller, highly biocompatible, and frankly, much, much smarter.
Now you might be wondering, why do scientists care so much about this? Well, it comes down to a really surprising biological fact. Cancer cells actually run consistently hotter than their normal surroundings. Figuring out a single cell's exact internal temperature isn't just some fun physics trick. It's absolutely crucial for characterizing how biological systems work, and honestly, it could completely revolutionize how we diagnose diseases. But to map those tiny, localized temperature differences, we need flawless, absolute precision.
Okay, so here's our roadmap for the explainer. First, taking cancer's temperature. Then, the quantum thermometer problem. Third, building a better sensor. Fourth, reading the quantum spin. Fifth, the deuterium breakthrough. And finally, the future of nanosensors.
Section 1. Taking cancer's temperature. The big dream in this field is to accurately map the internal environments of living biological systems, and that brings us to an incredible finding. When researchers tested a new quantum measurement method right inside the cytoplasm of living cancer cells in vivo, they found that the intracellular temperature was, quote, consistently higher than the surrounding medium. This physical proof grounds all this complex quantum physics into real, tangible biology. But actually getting that specific data reading, that was a massive technical hurdle.
Section 2. The quantum thermometer problem.
To measure temperature at this kind of microscopic scale, you need a quantum-level tool. For a long time, the standard method used nanodiamonds, which relied on something called nitrogen vacancy, or NV defects. Basically, scientists would take a diamond lattice, pop out 2 carbon atoms, and replace one with nitrogen. The quantum spin state of that resulting vacancy reacts to local magnetic fields and temperatures, letting scientists extract data from how the diamond fluoresces. It's a brilliant idea, for sure, but it has a major practical flaw.
The problem with those old nanodiamonds is that they're structurally inhomogeneous. Because those engineered defects are kind of random, the optical spectra they give off varies wildly from particle to particle. That randomness introduces unacceptable errors when you're trying to measure at the single particle level. But enter the MoQN, or molecular quantum nanosensor. These new sensors are structurally homogeneous, yield perfectly identical spectra, and rely on 0 structural defects. It is a total game changer.
Section 3. Building a better sensor.
This massive breakthrough in materials science comes from a team led by Nobuhiro Yanai at the University of Tokyo and Hitoshi Ishiwata of Japan's National Institutes for Quantum Science and Technology. So how exactly do you build a flawless, defect-free quantum thermometer? Well, first, the core. Pentasene molecular spin qubits. These are embedded perfectly inside our second ingredient, para-tarphenyl nanocrystals. This design makes the whole structure wonderfully uniform, preserving the delicate quantum coherence. Finally, to make sure a living cell doesn't just reject it, they coat the whole shebang in pluronic F127, a biocompatible surfactant. It is built cleanly and perfectly from the ground up.
Section 4. Reading the quantum spin.
Okay, so we have a perfectly uniform nanosensor operating safely inside a living cell. But how do we actually extract the temperature reading? They use a technique called optically detected magnetic resonance, or ODMR. This is the method used to detect the spin direction of molecular qubits. Think of ODMR as our translator. It's the vital technique that turns invisible quantum states into actual, readable scientific data.
The mechanics of extracting this data follow a really beautiful, precise sequence. Step 1. The researchers target the pentasene qubits while they're in an excited triplet state. Step 2. They use ODMR to detect the specific spin direction of those excited qubits. In Step 3, by analyzing that data, they pinpoint the exact ODMR peak position. Because the properties of these qubits change so predictably with heat, finding that peak position literally translates to the exact absolute temperature of the cell's interior.
Section 5. The deuterium breakthrough.
Of course, scientific progress is rarely a straight line. Just when the team thought they had the perfect sensor,
They hit a massive wall. While the sensors were completely uniform, the ODMR spectra were coming out blurred. Why? Well, the electron spins of the molecules were interacting with ordinary hydrogen nuclear spins inside the sensor. These hyperfine interactions were blurring the readings and completely threatening the precision of the entire project.
To solve this noisy bug, Hitoshi Ishiwata proposed a brilliant surgical chemical swap. Just replace the noisy hydrogen atoms within the molecule with deuterium. And you know what? That tiny little modification successfully suppressed the hyperfine broadening. It allowed them to read the ODMR spectra with unbelievable precision. This elegant fix was the missing puzzle piece, leading to their incredible success recently published in the journal Science Advances.
Section 6. The future of nanosensors.
So, we now have a chemically versatile platform for quantum sensing right inside living cells. But we aren't done yet. The technology is still evolving. First up, for the next frontiers, while MAU-QNs can measure the general interior of a cell, they can't yet target specific organelles, those tiny organs within the cell, like the nucleus or the mitochondria. Endowing the sensors with a targeting GPS is a major future challenge. Second is size. Right now, these sensors are about 200 nanometers across. That's unfathomably tiny to us, sure, but to go deeper into biology and be even less intrusive, shrinking these particles down further is going to be absolutely crucial.
And that leaves us with this final, profound question to consider. How will measuring the quantum temperature of a single cell change the future of disease diagnosis? When we can perfectly map the absolute heat signatures of malfunctioning biology at a microscopic level, entirely new worlds of medicine and treatment open up. I really hope this explainer helped you see the brilliant mechanics behind this quantum breakthrough. Thanks for learning with me today, and keep asking the big questions about our microscopic world.